Yeah. All right, so linear, we can make the definition as long as we want, but linear essentially is just a straight line. So what do you think nonlinear is?
A non-straight line.
Not a straight line. Okay. We are going to do this by columns. This first column is just going to help us talk about what a linear function looks like. Okay. We're going to start by graphing a linear function. So we're going to do 1, 1, copy these down, 2, 2, 3, 3, and 4, 4.
You said 1, 1. 3, 3. 4, 4.
That's my height.
Well, you're 4, 4.
I'm 5.
Okay.
All right. So graph 1, 1, go over 1 up 1. 2, 2 is over 2 up 2. 3, 3 is over 3 up 3. And 4, 4 is over 4 up 4. What do you notice about these ordered pairs?
Straight line.
It's a straight line. Now, if you were asked to graph the function, you would draw a straight line across and through those points, showing that it extends off into both directions. Yes. Draw the arrows. All right. So we can tell that this is linear just because it is showing that they're traveling in a straight line. We read any graph from left to right. It's never going to change. So if we start on the left side of this graph, that's over here, and we follow this line, is it increasing or decreasing? Is it going up or down? It's going up, so it is increasing. We always read left to right. All right, now, if we're looking at a table, how can we tell if a table is linear or nonlinear?
If it's constantly going up.
We're looking for something that's consistent, okay? So just like these ordered pairs, each value increased by 1 every single time. Whatever this x value is changing by should be the same, and whatever the y value is changing by, it should be the same. And we're looking for a ratio. We're looking for a constant rate. So what is this happening here? We're adding 2. And the next one, adding 2. And from 2 to 4, we're adding 2 again. So that's consistent all the way across. On the bottom, what are we doing? Subtracting 1 or adding a negative 1. Negative 1, negative 1. Now, whenever you're comparing these to make sure that you're getting the same ratio each time, because they can skip numbers trying to trick us, we want to set it up where it's the change in the y value divided by the change in the x value. So now what does that look like? The change in y over the change in x. We're just looking at it as a fraction, okay? So all of these have the same fraction. This is the y value is changing by 1, and the x value is changing by 2. And it's the same for all 3. So we know that because it changes the same amount every single time, that it is linear. All of these are on this side are going to be linear. Okay, so linear has a constant rate. The rate is negative 1/2. We also will be calling it slope in the future. It would be the slope on the graph. All right, now, what do the equations look like? So just like we can look at equations and tell how many solutions it has, we can look at an equation and tell whether it's linear or nonlinear. Okay, so equations are linear if they do not have exponents or a denominator variable. What that means, a variable in a denominator. It cannot have those two things if it's going to be a straight line. So, for example, and write these underneath so you have examples to look at. If you have y equals 2x, That is linear. It will be a straight line. We know that because this is our slope of 2. It's a constant rate of 2. So remember that that's still rate. So if we were to make a chart, a table, the constant rate between numbers would be 2. Also, if I write y equals x, does it have an exponent? Does it have a denominator? No, so it's still linear. If I wrote y equals 5x plus 3, that's still linear. As long as it doesn't have these two components, it's linear.
As long as it's what?
As long as it does not have an exponent or a variable in a denominator, it's linear. It can have a denominator, it just can't be a variable. So example, y equals x over 3 plus 2. The denominator is not a variable, so this is still linear. All right, now, what does a nonlinear function look like on a graph? Okay, so the next column is going to be titled nonlinear. I will in a second. All right, so the ordered pairs that we're going to put on this graph, let's go ahead and put 1, 1, 2, 3, 3, 7, and 4, 2. So ordered pair 1, 1, 2, 3, 3, 7, 4, 2. And we can tell that that's not a straight line.
This one, we don't gotta draw it all into the other.
We don't have to. We don't know what it's going to do after that. All right. So now if we're looking at a table that's nonlinear, you're going to look at the change in between every single value. So from 1 to 0, they subtracted 1. From 0 to -1, they subtracted 1. And -1 to -2, they also subtracted 1. So far it checks out. But if you look at the bottom, the change in y, this is decreasing by 2, and this is decreasing by what? 3. And once again, it decreases by 3. Okay, all it has to do is fail it once, though. Remember, we put it in order of change in y over change in x. So is -2 over -1 the same as -3 over -1?
No.
They are not equal. Make sure you write not equal. So it's nonlinear. That's just the symbol we use instead of writing the word change. We write delta.
Hey, bruh.
Okay? All right, now I want to write some examples of an equation that's nonlinear. So if I write y equals 3x squared, that's going to be nonlinear. Why? Exponent. How about y equals x over 5 plus x to the second? Why is this one? Why is this one nonlinear? Exponent. Y equals 5 to the x power. What about this one? Still an exponent. Even if the exponent's a variable, it's nonlinear. Y equals 3 over x plus 2. What's wrong with that one? Variable in a denominator. We can't have the variable in a denominator if it's going to be linear. So all of these are nonlinear.